But in the simplest terms, any problem in complexity is something that Einstein and his peers can't do. So let's imagine, if the clicker works, there we go, Einstein's playing a game of snooker. Now he's a clever chap, so he knows that when he hits the cue ball, he could write you an equation and tell you exactly where the red ball is going to hit the sides, how fast it's going and where it's going to end up. Now if you scale these snooker balls up to the size of a solar system, Einstein can still help you. Sure, the physics changes, but if you wanted to know about the path of the Earth around the Sun, Einstein could write you an equation telling you exactly where both objects are at any point in time. Now, with a surprising increase in difficulty, Einstein could include the Moon in his calculations. But as you add more and more planets, Mars and Jupiter say, the problem gets too tough for Einstein to solve with a pen and paper. Now, strangely, if you, instead of having a handful of planets, you had millions of objects, or even billions, the problem actually becomes much simpler, and Einstein's back in the game. So let me explain what I mean by this, by scaling these objects back down to a molecular level. Now, if you wanted to trace the erratic path of an individual air molecule, you'd have absolutely no hope. But when you have millions of air molecules all together, they start to act in a way which is quantifiable, predictable, and well-behaved. And thank goodness air is well-behaved, because if it wasn't, planes would fall out of the sky. Now, on an even bigger scale, across the whole of the world, the idea is exactly the same with all of these air molecules. It's true that you can't take an individual rain droplet and say where it's come from or where it's going to end up, but you can say with pretty good certainty whether it's going to be cloudy tomorrow. So that's it. In Einstein's time, this is how far science had got. We could do really small problems with a few objects, with simple interactions, or we could do huge problems with millions of objects and simple interactions. But what about everything in the middle? Well, just 7 years before Einstein's death, an American scientist called Warren Weaver made exactly this point. He said that scientific methodology has gone from one extreme to another, leaving out an untouched great middle region. Now, this middle region is where complexity science lies, and this is what I mean by complex.
Have you ever wondered how thousands of birds move in amazing patterns like this? Ever watched fish schooling and wondered how they coordinate their movements? When you're looking at a flock of birds or a school of fish, you're watching the behavior of a system of many interacting parts. In this case, individual birds or individual fish are the parts. Systems where unexpected patterns emerge as a result of many individual parts interacting are called complex systems. The study of complex systems has recently been recognized as a new type of science. The living world is a great place to find examples of complex systems, where the actions of individuals turn into the behaviors of a group. So, other than the fact that they're really cool, why is understanding complex systems important? Biologists, physicists, engineers, mathematicians, and social scientists are finding that the rules that create ordered systems from individual behaviors are showing up in many fields and at many different scales, from molecules in our bodies to bird flocks to human interactions like crowds and traffic jams.
About because people have begun to realise that we can use and exploit analogies between our human systems and those of the physical world around us. Now, to give you an example, the incredibly complex problem of migration across Europe. Actually, as it turns out, when you view all of the people together, collectively they behave as though they're following the laws of gravity. Now, but instead here of planets being attracted to one another, it's people who are attracted to areas with better job opportunities, higher pay, better quality of life, and lower unemployment. And in the same way as people are more likely to go for opportunities close to where they live already, London to Kent, for example, as opposed to London to Melbourne, the gravitational effect of planets far away is felt much less. So to give you another example, in 2008, a group in UCLA were looking into the patterns of burglary hotspots in a city. Now, one thing about burglaries is this idea of repeat victimization. So if you have a group of burglars who manage to successfully rob an area, what they'll do is they'll tend to return to that area and carry on burgling it. So they learn, the layout of the houses, the escape routes, and the local security measures that are in place. And this will continue to happen until local residents and police ramp up the security, at which point the burglars will move off elsewhere. And it's that balance between burglars and security which create these dynamic hotspots of the city. Now, as it turns out, this is exactly the same process as how a leopard gets its spots, except in the leopard example, it's not burglars and security, it's a chemical process that creates these patterns in something called morphogenesis. Now, we actually know an awful lot about the morphogenesis of leopard spots. Maybe we can use this to try and spot some of the warning signs with burglaries, and perhaps also to create better crime strategies.